Right, good morning everybody. So last time we got to the stage of, let me first say something about textbooks. Somebody asked me at the end of the lecture about books, and if you look in the first year course handbook, there's an appendix which gives recommended textbooks for every lecture course. And there are two textbooks down for this course, which I think are both excellent. There's an Oxford one and a Cambridge one, OUP and CUP, and I think and they're both quite modern. One is 2010, the other's 2013. I think either of those would be entirely reliable and probably more reliable than me. It didn't take much web searching to find a website with the complete text of the Oxford book on the open web. So OUP has missed a trick there, because that's the kind of thing they're usually rather keen to avoid. But nonetheless, you don't have to buy it if you don't want to. So we got as far as considering a single variable which we'd measured lots of times, and all those measurements were taken with the same apparatus in the same way. So there was nothing to distinguish the data. There's no objective reason to prefer one of those measurements over any of the others. We might have subjective reasons to prefer some, or at least to dislike others, because they're outliers. We're not really allowed to, in fact, we are not allowed to take that into account unless we can introduce some objective evidence that distinguishes one measurement from another. The outlier is an important aspect of the data. It may be not giving you so much information about the centre of the distribution, but it is telling you about the width of the distribution, and that is telling you about the accuracy of the whole data set. So outliers are important. You can't throw them away. There has to be a very high bar before you can throw away a measurement without some objective reason for disbelieving it. You can't just cherry pick the numbers. That's simply, and in the last lecture I will show you why you can't do that. It's not a moral prohibition. It's just stupid, because it just leads to getting the wrong answer. Okay, and I'll show you why that is. So we just posed, given that set of measurements, I just posed three questions. How accurate are the measurements? What's the best answer if by combining the measurements, and how accurate is the best answer, which is presumably more accurate than the answer to question one. And I drew attention to the fact we're basically working with the equation at the bottom of the previous page, where each measurement could be viewed as a true value plus a systematic error plus a random error, but actually we're not going to make any progress with a systematic error by statistics. We've got to approach that by different means. So for statistical purposes, we're going to write that equation like this, that each data measurement is the average of our experiments plus a random error. Okay? So x differs from the true value of the thing we're trying to measure by the systematic error. But that's a separate question. We're now just dealing with statistics. We're not dealing with systematics. And we introduced the idea that this angle bracket is a kind of counterfactual thing. If there are any second year P&Ps here, I know this is on their lecture list, they should probably prick up their ears at this point, because this is an average over all possible measurements, not the measurements that you've actually taken. So there's something definitely counterfactual about that, and it means that it's why the value of the true value and the errors remain unknown, because we can never really get a handle on the true value. We can only make estimators for it. However, on average, they'll be 0. That means that it's a random unbiased variable, and the randomness includes the idea that any systematic pairing up of the variables will lead to products that average to 0, essentially because positives and negatives will occur with equal frequency. And so the one thing that doesn't give a value for is epsilon I squared. You see there's an explicit I not equal to j here, so that doesn't tell us anything about the average of the square. And of course the average of the square can't be 0 because the square is positive definite. And so all we can say is that the average value of epsilon I squared is some number, and that's a very important number. It's a measure of the width of the distribution, and it's called the variance. Obviously, because if x has dimensions, it's a length, it's a mass, it's a charge, whatever it is, this has that dimension squared, but it's the squared width of the distribution, and there are various notations for it. I'm calling it big V sub x, to show that it's the variance of the x, and we'll meet variances with different subscripts for different for the variances of different distributions. Another notation that's commonly used is var x. So it's one of these things like sine and cos and tan, where you give it a little name rather than a symbol. And its square root, the square root of the variance is now going to have the same dimensions as the thing you're measuring, and that is this population standard deviation. So the best answer to this, the individual measurements, is the population standard deviation. The population standard deviation is the accuracy of the measurement. The question is, how do we use the data that we've got to estimate it? And that is the standard estimator for the population variance using, on the assumption that all the measurements have equal validity, as I've just described. And it's very like what you would normally call the standard deviation of the numbers that you've just put up. It only differs in one respect, or the square of that. That's the standard deviation there. The square of that, the only thing is that we've replaced n in the denominator with n minus 1. Now, the reason for that is to do with degrees of freedom. The data is being used here for two different purposes. It's being used to establish a mean, a best value, and a spread, which means that if we use, so essentially one linear combination of the variables x is being used to determine the mean, which means there are only n minus 1 independent linear combinations of those numbers with which you can determine the spread. And so we only have n minus 1 measures of the spread of the distribution. And so the division here is by n minus 1. I shall prove that in the last lecture, probably. That is to say that it's on the sheets, but whether we'll get to it, remains to be seen. Right, so that's the accuracy of the measurement, and the best result is the population mean, sigma xi over n. Now, other means are available. So there's a thing called a weighted mean, where this is a special case of a weighted mean. So x bar would be the sum of some weights, wi, times xi, divided by sigma wi. So if we like some measurements better than others, for some reason, something which I've just said we're not allowed to do, we give them high weight in this sum, and other measurements we give low weight. And then if the weights are all equal, then this reduces the form that we've just got up there. If all the weights are 1, then sigma wi is just n, and this becomes sigma xi over n for the ordinary mean. So the ordinary mean is called an arithmetic mean. This is called a weighted mean. And it's very occasionally the case that that is the right procedure to follow. I think it's much more often the case that it's not. One of the questions on the problem set, let me just bring up the problem set. The mean as a minimum variance estimator, question 4, shows that if you combine the data in this way, you get you'll get, on average, you'll get the right answer, but the error on the answer will be bigger than if you'd use an ordinary mean. If the values coming in are of equal weight, are of equal accuracy, then the optimum way to combine them is the way it's said on the lecture notes, and that a weighted mean will not give you a wrong answer, it will give you a less accurate answer. That looks at the thing in a bit more generality as to how to combine data, how to assign weights in the case of unequal errors. Now, as I mentioned at the outset, the final result, the mean here, ought to be more accurate than individual measurements. That was the reason for taking all those measurements in the first place. And it's actually the variance is n times smaller. So the variance for the mean, so here's a variance symbol with an x bar instead of an x attached to it. The variance of the x bar is the variance of the x divided by n, and if you work that through, the sigma is that. And this is called the standard error, and that's the thing that is many lab scripts refer to standard errors, and that's what's meant by it. So it has a division by an n and an n minus 1, and is more accurate than the individual measure, and is giving a result that's more accurate than an individual measurement. The important thing about a standard deviation is that it is not an error limit. It does not encompass the data. It's the average of the squares of the errors, which means that some errors are bigger than sigma and some errors are smaller than sigma. Even in the data set that you've got, the sigma will be, the x bar plus or minus sigma will not encompass all the data in the data set. It can't do that because it's the root mean square error. So in order to give a coverage, which is a different thing from a standard deviation, you have to multiply the standard deviation by a coverage factor. So if you want to give something that encompasses the data, the whole likely spread of the data, you have to multiply the standard deviation by 2 or 3. And that's called a coverage factor, and if you're doing that, you should certainly say that you're doing it. So I'm going to use another example from Robert Millikan here. After he'd finished doing the oil drop experiment, not being a man of small ambition, he tackled probably the hardest problem in experimental physics at the time, which was trying to get accurate measurements out of the photoelectric effect. The reason that he did that was very clear. He wanted to prove Einstein wrong. If you read the introductory paragraph, it's quite... I mean, the whole paper, and especially the theoretical bit at the end where he discusses his results, he's wrestling with the fact that he was desperate to prove Einstein wrong. It was obvious that Einstein was wrong because electromagnetic theory was a beautiful theory, and Einstein said, well, actually, it's not going to work. We're going to have to throw it away, and we're going to have to introduce something with quantum in it. And he said, no, we can't do that. That's not right. And anyway, Einstein didn't say what this new quantum theory was. He just said we needed it. He starts off by reviewing the experimental situation, and this is the Einstein photoelectric equation. So I assume you've all come across. This is one of the famous 1905 papers of Einstein. He said that the process of the photoelectric effect. So here's a metal surface. Here's a photon coming in. It ejects an electron, and the energy of the kinetic energy of the ejected electron plus the energy, the work needed to get it out of the metal, has to equal the energy of the photon that you put in. So the energy of the photon is divided between energy needed to extract the electron from the metal and then some kinetic energy that's given to it so that it escapes. This means that this isn't zero. The electrons are bound into the metal by some energy or other. They don't just fall out. So there's some minimum value of that, which is called the work function, which corresponds to a maximum value of that, which means that there is a maximum velocity of the ejected electron. And that means that if you apply a reverse electric potential so that the electrons are being repelled by the metal plate that's collecting them, there will be a voltage at which they cannot reach the metal plate, which will stop the... So if you're collecting this current on some collecting bit of apparatus, and then you're then measuring the current, there's some voltage in here somewhere. This is a rubbish diagram, which is going to stop the current entirely. Now, that simple theory, which I'm assuming you've come across before, so there's the Einstein photoelectric equation. Millikan said it had 4 pieces to it. For each frequency of light that you apply to the metal, there's a maximum velocity of emission. That maximum, there's a linear relation. So that maximum velocity means that there is a stopping potential at which there is no photocurrent. There's a linear relation between the stopping potential and the frequency. The slope of that is related to Planck's constant over the mass of the electron, and there's a minimum frequency of the radiation which is capable of ejecting electrons at all. Because if this energy here is less than the work function, because then there won't be any photoelectric effect for that reason either. And there's a thing about contact EMF, which turned out to be very important in his investigations, which he'd also looked at. And he considered that every single one of those points was unclear, uncertain. There was recent work which denied the validity of the relevant point. So he thought that the entire theory was completely open. There was no experimental evidence for it all, and he could go in there and prove it wrong. And he built the most amazing piece of apparatus. This was done in Chicago, and there's a lovely picture of it somewhere. There it is. So you can't get much of an impression from that. All you can see is that there are things in all in 3 orthogonal directions. There's a rather better diagram on a couple of pages later. Here it is. Right. So this is a glass apparatus, an evacuated glass tube, and somewhere out of the plane of the paper is the best pump, the best vacuum pump that he could buy. This thing in the middle is a little a rotor carrying 3 slugs, 3 cylindrical discs of different alkali metals. So he might have a sodium and a potassium and a lithium mounted in there. This is the window through which the exciting radiation will pass, and the dotted line inside it is a copper mesh which is collecting the electrons. So there are terminals here connected to the copper mesh which are collecting the photocurrents. So this is all inside the vacuum system. He can rotate the rotor in the middle with an electromagnet. He can also advance this knife here so that he can, if he rotates this disc round here, he can advance the knife and then rotate it and take a shaving off the top surface of the metal, which of course, as you may realise, is very, very reactive. So he can get a nice clean surface, and this is a special device for measuring the contact potential. So he describes this as an experimental laboratory in a vacuum system. It's an extraordinary piece of apparatus. And he was able to show that Einstein's equations were exactly right, in every particular, which was a source of great grief to him. And there's several pages at the end of the paper where he laments what on earth are we going to do if Einstein's right. If I just come back out of this and go back to the lecture notes. So the first question was establishing the linearity, and that required taking measurements at a range of frequencies and showing that it was linear. Actually, no, the first problem was showing that there actually was a stopping potential, that there was a reverse bias that you could apply to that collector plate which stopped the photocurrent. Even that was unclear at the time he did the experiments, and he was able to demonstrate with some brilliant experimental technique that that was because they weren't using adequately monochromatic illumination. The radiation coming in was contaminated by shorter wavelength radiation, which they hadn't blocked out, or hadn't filtered out adequately carefully. And once the main photocurrent, due to the exciting radiation, which is the main part of what they were illuminating it with, was stopped, there was a residual photocurrent due to this shorter wavelength radiation, which continued unchecked. And he showed that if you carefully eliminated the stray light so that there wasn't this shorter wavelength radiation contaminating, then even if you had a very, very large photocurrent, when if you turned up the voltage, you got absolutely none. And having shown that, he showed that there really was genuinely a stopping potential. You then have to show it's linear. You have to show that you have to measure the stopping potential for a range of different frequencies. And that was his first method. And then the slope of the line is given by h over e, as you get by, you have to, this becomes, if the stopping potential is v, the stopping potential becomes that. And that gives you that the stopping potential is W min minus W min over E plus H over E times nu. So the slope of the line between the stopping potential and the frequency of the light is Planck's constant divided by the charge. So he first of all he demonstrated it was linear, and that's his first method. And I'll come back to that when we've done a straight line fit, because that involves doing a straight line fit. However, he thought that this involved taking an extended period of measurements on the same surface. And he knew that these surfaces, even in the best vacuum that he could make, were not stable, that they slowly oxidized, or at any rate, the surface changed in some way. And that had the effect that the work done to extract the electron kept changing. And so using the stablest surface he could get, which he found was not a cleanly cut surface but an old surface, an aged surface, which had stopped reacting, then he could do that. But he thought a more accurate way to get out h over e, knowing that it was linear, was just to measure 2 points on the line as quickly as he could. And that would remove if you did it quickly enough, it would remove the change in W. And he did that by using two frequencies, A and B, and taking a sandwich of measurements using A and then B and then going back to A again, and using for the A value, for the stopping potential, the average of the two that he got. And that effectively cancels out the linear change in the stopping potential over the time that it takes to do that. And he reckoned he could do that in 5 minutes. So using different frequencies, all these different frequencies here, if you work them out, they're in the blue and ultraviolet region of the spectrum, I think. And they're all different spectral lines of some element or other. I forget what he was using for his light source. Wait a minute. So no, I've actually done the calculation. So you take the difference of the voltages between A and B and the differences of the frequencies between A and B, and these are the slopes that he got. So these are different values that he's obtained for the slope, all taken by the same method at the same time, And it's just an example of a data set that you can take the mean, the population standard deviation, and the standard error. And I've given those quite accurately there to 3 decimal places, which is more than you need to express the result. The result is here, 4.13 brackets 3, but I've given another decimal place here, so that because many people have calculators with statistical functions, and they're often a bit vague as to what the difference, and it may give them different sigma options and so on. So if you just put that set of data into your calculator and press all the right buttons, you should get exactly those numbers. And if you get different numbers from that, then your calculator is giving you a different sigma. Because there are a range of different standard calculations that people can do given a data set, and these are the particular ones that we want, are these ones. Okay? Now, he was right that that was more accurate than the other method, and if you view it as a measurement for h over e, it's extremely accurate within the, I mean, it's slightly better than 1%, it's 0.7%, and it's absolutely spot on to the modern value. Of course, he thought he just measured e, and he viewed this as a measurement of h. That was a bad move, because, of course, he got the wrong answer for e, as we'd discussed last week, and therefore he'd also got the wrong answer for h. So this is an example of what I said last week, that different combinations of the physical constants ended up getting contaminated by Millikan's value for e. Right. So that's just how you analyse a single set of measurements of the same thing. Very often, in fact almost invariably, the thing that you're measuring isn't the thing you're trying to work out. It's the input value to a function. And so there's some functional relationship, which is sketched here, between the thing that you've just measured, which is x, and you've got the value a, with some standard deviation dA, which is shown here with 2 red lines. And what you're interested in is some function f of a. And so if as it were, 68% of the numbers that you've obtained are between the 2 red lines, then 68% of the numbers will be within the 2 red lines up here, which is fa plus the standard deviation for f, df. Okay? However, it's perfectly obvious from the diagram that dA and df, I mean, I've given them those names for a good reason, they're obviously related by the slope of the line, the slope of the function, at the point that we've measured. So it appears that the standard deviation of the value that you get for f of a, sigma f, that standard deviation is related to sigma a by df dx evaluated at a. That's almost right. The only problem is what happens if the slope's negative. Well, of course, we need a positive number here for the standard deviation. So in fact, here it must be minus the slope. Okay, the range here is related to the range here by the negative of the slope because the slope's negative. So it must be the modulus of that derivative that relates the a with the f. And more fundamentally, in fact, remembering that all standard deviations are really square roots of variances, the real relationship is between the variance of a and the variance of f, which is given by that. So this is and the effect of the modulus is simply the effect of taking the square root of that equation to get this equation. When I was demonstrating, which I don't do now, but when I did, I was always often asked for this equation because students couldn't remember it. And the equation is relatively straightforward, but my intention in drawing these pictures is that you'll find the picture more memorable than the equation. So it's a perfectly obvious geometrical relationship between a range on this axis and a range on that axis, and the relationship, the ratio between them being the slope of the function. I mean, it's the intention of drawing the diagram is to make the diagram more memorable than the result, because the diagram tells you the result. And another way of thinking about it to make it memorable, I think it's important that some things are memorable, and this is one of them, is to think about the dimensions. Suppose this is a length, and this thing over here is an area, okay? Or is some function with different dimensions. So this has dimensions of x, f has the dimensions of f, sigma f has the dimensions of f, and so they have to be connected by something with dimensions of f over x, which is df dx. Okay, so the dimensional argument is another way of reinforcing that basic result. So that process of taking an error on one variable and transferring it to an error on another variable is called propagating the error. And so here are some very simple examples. If this is the function of a, then this is the standard deviation. So the first one is entirely obvious. The second one is slightly less obvious. So let's work through that. So f of x is 1 over x squared, and then df by dx is, sorry, was that what I had? No, I had 1 over x, was k over x, was k minus k over x squared, and that tells us that sigma f is, so df by dx evaluated at a is minus k over a squared. So if I put that in the formula, I get the modulus of that. Now a squared is presumably positive definite, so that is modulus of k divided by a squared sigma a. Okay? So that's the second one, and then the third one and the fourth one are simple examples along the same lines. Note that the sigma a divided by a is actually the fractional error in a. So this is a number. The dimensions here cancel top and bottom, of course. So that's just a number, and it's just some percentage. It might be, I mean, if it's 0.007, then it's 0.7%. And it's obvious, looking at students' work in the laboratory, that a lot of people have been trained up very rigorously in fractional errors. They do everything in percents. And there are purposes for which it's useful, and there are purposes for which it's not useful. And if you've come from that tradition, I urge you to not be bound by it, but to step outside it and look at other ways of doing things. But another way but the fractional error is the error in the logarithm, which is one of its important features. So that's the first stage of taking an experimental measurement and using it for something else. The second stage is to combine two numbers or two values which you've measured, which have errors, as inputs to a function. So this was as it were, the first one was a function of one variable. You've measured the variable, you know the function. Now we've got a function of two variables. We've measured both variables. We can put them into the function and calculate the answer. So I'm going to start with a trivial example, and then we'll generalize it to the general case. So we've measured A, and the value that we've got, it differs from the true value by its error, and on average, averaging over many different experiments. Now that is sigma a squared, and similarly for B. Okay, so we've got these two values A and B, and we want to calculate A plus B, and that's the simplest possible case that we can take. Now if we just add together these equations, we get A plus B is the sum of the true values, which is the true value of C, plus the error in A, plus the error in B. Okay? So the error in A plus B is the error in A plus the error in B. That's blindingly obvious, isn't it? Okay, now the question is, so that was, what's the average value of that? Now, on average, so if we did this many times, calculated A plus B using experimental data many times, then each of these would average to 0, and on average we get the right answer. Okay, so the best possible answer for C is definitely the sum of our experimental numbers. However, the question is, what's the error on it? Now, the error on C is the error on A plus the error on B, and in order to calculate the error, we need to look at its variance. So we need to calculate the variance on C, and here it is. So it's that thing squared, and if you multiply it out, you get 3 terms. It's the average of A squared, which is the variance of A. It's the average of EB squared, which is the variance of B. And it's this extra term, epsilon A, epsilon B, which is called the covariance. And that's why, and it's the covariance that makes combining errors interesting, because it complicates things a little bit. So I'm using this sans serif notation for the covariance. Another notation, people who call it variance var will tend to call the covariance cov. And it measures some coupling in the two errors. It means, I mean, normally, if whether or not one error is positive or negative is independent of whether or not the other thing is positive or negative, then if you average that product, you get positives and negatives equally likely, and it averages to 0. So if the covariance is non-zero, there is some linkage between the two measurement processes that have produced the errors in A and B. So let's, for the moment, assume that the A and B were measured in completely separate experiments, so there really isn't any linkage between them, but you should look for subtle linkages like common calibration errors and so on. So let's just take for a moment the case where the covariance is 0. The opposite case would be where if B was in some sense calculated from A, or so tightly linked to A that the error is perfectly correlated, which means that the error in B is just some multiple of the error in A. So that would be an extreme of non-independence, that the two variables are not only on average related to each other, but they're strictly related to each other in every single case. Okay? If that's true, then the covariance, CAB, which way around do I find it, is alpha epsilon A, because epsilon B is alpha epsilon A, it's alpha times the covariance, the variance of A. Whereas VB is the average of epsilon B, which is alpha squared times the variance of A. So in these circumstances, the covariance is equal to the square root of the product. It's the geometric mean of the two variances. Okay? So that's the biggest that the covariance could be. So the covariance could be 0, or it could be as big as root VA VB. And so in general, the covariance must be some number times VA VB, where that number, R, is called the correlation coefficient and lies between -1 and 1. Okay? And so the So in order to analyse that more generally, you'd want to look, I mentioned that all of these things rest on some underlying probability distribution function for the results. And if we've got two results, we've got an A and a B, then we've got some pair of numbers for A and B, and in different possible cases we might have different possible pairs of numbers, and the question, and so you could define a joint probability distribution in the plane. The question is, what's the shape of that probability distribution, and if it's got a certain symmetry to it, and in particular if it factorizes so that it's just the probability of getting A and B is just the probability of getting A multiplied by the probability of getting B, then we're in the independent error case. But more generally, this distribution might actually be rather skew, so that the distribution is elongated in this direction, which means that large values of A are correlated with large values of B. And that's what the correlation represents. And the extreme of that, of course, is the perfect correlation case that I just mentioned, which means that the points that you get are all actually on a straight line. Right, so let's now look at the general case. So we're computing C, which is some function of A and B. All right? An arbitrary function which I'm not going to specify. And so the value that we get plus its error is given by the compute. We're putting in the value for A, which is the true value plus its error, and we're putting in our value for B, which is the true value plus its error, into the function f. And that gives the true value of C plus 2 error terms, because now this rests on a Taylor expansion of that function, which some of you may know and some of you may not know. Actually, just as a matter of interest, how many of you have met windswept derivatives, partial derivatives like that? And people not met them? Yeah, okay, so that's about half and half. Okay, so so this page is definitely not for everybody, but I'll come back to the independent case in a minute, which doesn't depend on it. Okay, so that's what we're doing. So that's the error term. It's the error in A times the partial derivative with respect to A, error on B times the partial derivative with respect to B. Now, that product, I'm now going to do some vector stuff. Now, you do at least know this, I think. That product, df dA times EA, df dB times EB, could be generated by doing the dot product of those two vectors, yes? So if I dot product those two vectors, I get df dA times EA plus df dB times EB. You're all seeing how to do that. So I could write that as G transpose E or E transpose G as just the dot product of those two vectors, yeah? So that's the scalar product, the inner of those two, the inner product, various different names it goes by. That's what epsilon C. That's what epsilon C is. So what we need to know is the variance will be that squared, and I've shortened that calculation slightly. So let me fill in all the steps. So the variance of C is G transpose times, on average, the expectation value of E times the expectation value, well, of epsilon transpose times G. Now, this thing in the middle, epsilon times epsilon transpose, that's not a dot product. That is a, that's epsilon A, epsilon B, epsilon A, epsilon B. That's not a dot product. The two vectors are back to front. What do we get if we multiply the vectors? Can we actually do that? So are we allowed to do that kind of matrix multiplication? Well, yes, we are, because the number of columns of this matrix, which is 1, is equal to the number of rows of this matrix, which is also 1. And so if I just multiply that out, I'll get a 2 by 2 matrix, which is epsilon A, and then epsilon A, epsilon B, and then epsilon B, epsilon A, and finally epsilon B, epsilon B. Okay? We get that matrix, and then so in order to find the value, the variance, we need the average of that. And you can see what the things that, so the average of this element here is the variance of A, the average of this element here is the variance of B, and the average of these are the covariances. So what we've ended up with is the general result for computing the variance in a function of two variables, and this generalizes to any number of variables in a perfectly obvious way. We need the vector of derivatives here and here, and we need the variance-covariance matrix between the measured values. And given all that information, we can propagate an error. We can combine the errors on A and B to produce the value C. So that is the general result for computing a variance of two values from coupled errors. Right, so now I'm going to leave coupled errors behind and concentrate on the much more common case where the errors are uncoupled. Okay? So if they're uncoupled, then these off-diagonal terms, the covariances, are 0. So what happens to that equation if the covariances are 0? So we get df dA, df dB on the left. We get VA 0, 0, VB, and then we get df dA, df dB. And if you just multiply that out, so the next line in the sum will be df dA, df dB in brackets, and then we'll get VA df dA, VB df dB, and finally if we multiply it out we'll get VA df dA squared plus VB df dB squared. So the variance on C, so this is independent errors. We get the variance on C is VA df dA squared plus VB df dB squared. And similarly for the so if we take the simple case that we started with of a simple sum, so f is just a plus b, df dA is 1, df dB is 1, and we just get sigma a squared plus c. We get the variance of c is variance of a plus variance of b. So the standard deviation of c is the square root of the sum of the standard deviations. Now this brings me back to the point I made earlier. If you've been rigorously trained in this percentage error tradition, this isn't much help to you, because this is not a percentage error. This is an actual error. So in this formula, percentage errors aren't any help. We need to know what the actual errors are. Okay? And that process of squaring and adding and taking the square root is called adding them in quadrature. So here's some more simple examples of, so here's the one that we just worked through. C is a plus b, sigma c squared. So here's the general formula that I just wrote out. Sigma c squared is the partial derivative times sigma a squared plus the partial derivative times sigma b squared. That's the case that we've just worked through. If we put in c equals a minus b, the partial derivative with respect to b is minus 1, but it still gets squared here. It doesn't make a jot of difference. Whether you're taking the sum or the difference, the error still gets bigger. And that's actually a useful bit of experimental information, that if you're evaluating something by taking the difference of two numbers, the number gets smaller, but the errors get bigger. So evaluating a thing by a difference it can be a very bad way of doing it, okay? Because the more interesting case is the product, and I'll work through that. Okay, so C equals AB, and so dF by dA is B, and dF by dB is A. And so sigma C squared is B squared sigma A squared plus A squared sigma B squared. Now, there's a slightly more memorable way of saying that. If I divide both sides by A squared B squared, I get sigma C squared over A squared B squared is sigma A squared over A squared plus sigma B squared over B squared. But AB here is just C, and so this side of the equation we could write as sigma C squared over C squared. So the fractional error squared in C is the fractional error squared in A plus the fractional error squared in B. So for products, percentage errors is just what you want. So if you want to combine a 1% error with a 3% error, sorry, if you want to, no, I can't do that in my head. If you get a 1% error and a 3% error, we need, we'll get a root 10, we'll get a 3 and a bit % error, okay? If you want to combine a 1% error and a 1% error, you get a root 2% error, you're 1.4% error, okay? So that's the answer for the quotient. Now that's really where I wanted to get to today, so I think I'll stop at that point. And next week we have 2 lectures, and the first one will be about essentially straight line fitting, or more generally functional fitting. Right.